Hello, Physics Nation. My name is Nate Larmond, and I'd like to share my results from the do-it-yourself wheel and axle construction project. This is actually my second prototype. Get some cardboard, tape, glue, string, a pair of scissors, and a pencil, and you are good to go. There's nothing wrong with grabbing a wheel and axle you can find, like a toy or a tool. That's cool. You can analyze a pre-made machine, but it's fun to build and make mistakes and fix those mistakes. I recommend building this system, and you can actually do all sorts of crazy experiments with low friction pulley like we have here. Anyway, here's my little YouTube construction video. Let's watch this. I made the big stack of coins the input, and I made the little penny the output. I sort of reversed the normal way you use a wheel and axle. Wheels and axles are usually made to multiply torque, that is, they're force multipliers, but I made mine a distance multiplier. I wanted my load to go fast up, and I wanted my effort or my input to go slow down. So I just put the heavy weight on the pencil, that is the input, whoop, and there it is. It drops 2 inches. And here I am cranking. It's off camera, but there's a little crank. You have to lift up the input force, the big stack of coins, and now I drop it. And there's the penny flying up 22 inches. All right, so whoop, I lift the load 10 times as far as the input drops. But as you see, the input has to be a really, really big force. So simple machines never give you something for nothing. You can multiply force. That's a mechanical advantage greater than 1. Or you can multiply distance. That's what I did. That's a mechanical advantage less than 1. And as you'll see, much, much less than 1. So here's my little concept sketch, trying to review isometric views. We'll talk about, Z going off at 30 degrees above the horizontal and all that later. This is just an informal sketch. So here's my pencil. I am hanging 9 nickels and 2 quarters. That adds up to 56 grams. Now I know that's not a force. Technically, we should divide by 1,000 to get kilos, multiply by 9.8 to get newtons. But on the surface of the Earth, mass is proportional to, weight. So I'm just getting sloppy with my units here. Let's just pretend mass is force. They are not equivalent. They are proportional. So off of the big wheel, I wanted my output, 2.5 grams, a very small output force. So when you do load divided by effort, or output force divided by input force, you get 2.5 divided by 56, or 0.04 for the mechanical advantage, a very small mechanical advantage. But like I said, this is not a force multiplier. This machine is a distance multiplier, and it's basically a third-class lever. Here is how you should analyze the wheel and axle. Look at it from the cross-section. See how the fulcrum's in the middle, the axis of rotation? And then I hang the big stack of coins off the pencil. This is really tight to the fulcrum. It's only 1/8 of an inch away. So that's the effort. I had to hang a huge force off that pencil in order to lift this very small force. That was hung off of the wheel. Okay, so the effort distance in this case is the radius of the pencil, 0.32 centimeters, or 1/8 of an inch. And then the radius of my cardboard wheel, I measured to be 1 7/8 inches. That turns out to be 3.65 centimeters. So the ratio of distances, the ideal mechanical advantage is 0.32 divided by 3.65, or 0.087. And as you can see, that leads to a really horrible efficiency. The actual mechanical advantage divided by the ideal mechanical advantage, 0.04 divided by 0.08, is roughly a half. So half of the energy I put into this machine, half of the input work, the force multiplied by the distance, that huge load drop, is wasted, is not regained in that increase in the penny's gravitational potential energy. So where does all the missing energy go? Well, I wasn't real uptight about the way I made my so-called bearings. I just jammed a pencil through these four vertical cardboard rectangles, and you can see all of this cardboard tailings, I guess you'd say. I should probably clean those up, and then maybe it would spin more freely with less friction. Who knows? 50% efficient is not great. I'd like to analyze the torques now. So that's force cross radius. Again, you just need four measurements: input force, input radius, output radius, and you just multiply the input force by the input radius. Again, 56 grams is not a force. I know. I should divide by 1,000. That gets you to kilograms. Multiply by 9.8. That gets you to newtons. And, well, this should be meters. Actually, you should divide by 100 to change 0.32 centimeters into meters. But let's just be sloppy with the units. I don't want to get lost in the details. Probably already have 18 gram centimeters should be Newton meters of torque. All right, so weight equals mg. That's actually a special version of Newton's second law. Force equals mass times acceleration. The Newton equals the kilogram multiplied by the meter per second per second. Anyway, let's just, like Hans and Franz say, hear me now and believe me later, okay? Mass is proportional to force, not equivalent to force. Anyway, here's the input torque. Here's my big heavy weight acting at a very small distance, 3 millimeters. So that gives you 18 gram centimeters of input torque, so-called input torque. Let's find the output torque. All right, so this is a much bigger lever arm, 3.65 centimeters, but a very small force, 2.5 grams. The product of 2.5 and 3.65 is 9.1 gram centimeters of torque. So you saw the video. The system is not in equilibrium. So when you analyze the dynamics of rotational systems, you want to decide, is the system in balance or not balance? I tried to tune it so the load dropped at a constant velocity, so the system wasn't accelerating, but I think the system really was accelerating. Anyway, you can check out the video. The bottom line is, if a system is accelerating, it is not in equilibrium. So the angular version is the sum of the torques equals the rotational inertia multiplied by the angular acceleration. But if there's no angular acceleration, if it keeps rotating at a constant velocity, then the sum of the torques is 0. So what I did was I just added my two torques. Here's my input torque, negative 18 gram centimeters, and here's my output torque, 9.1 gram centimeters. Well, the negative is winning. The so-called, clockwise negative z is winning. It's beating the small output, the counterclockwise positive z. So there are two ways to interpret this. Like I said, perhaps the sum of the torques isn't equal to 0. Maybe when you let go, it gets faster, faster, faster. Or perhaps there's a third torque we're ignoring. Perhaps it shouldn't just be the two string tensions. Perhaps we should include a frictional torque. Anyway, we're going to talk about mu and friction later on. Thanks for watching. Make your own wheel and axle. See you in the next video.